So by request, here is an explainer video going over the intricacies of inverse trig. Now, off the top of the bat, we need to focus on the idea of what an inverse is. And if we go all the way back to chapter 5, an inverse simply was where we switch the x and y value. Switch x and y, then solve for y. That was the process of finding an inverse. We also, if you switch the x and y, we're also switching the domain and range. So that's the idea. What inverses do, inverses undo a function. For example, you guys often see the example of x squared, then the inverse of x squared. So if f of x is x squared, then f inverse is the square root of x. When you talked about f of x equals x squared and f inverse square root of x, we know that the domain for x squared is all reals, and the range y is greater than 0, equal to 0. But for the inverse function, our domain is x is greater than or equal to 0, and our range is y is greater than or equal to 0. And if we looked at the picture for x squared, we have our parabola with the vertex at 0, 0, and then the inverse of that function starts at 0, 0, but it's only half of a sideways parabola. And that was because it had to pass the vertical line test. And subsequently, for inverse functions to exist, they have to pass the horizontal line test. And so with x squared, we limited the domain in order for it to be invertible. And this was kind of taken at face value. There are some functions where we have to limit the domain in order for it to be invertible. And then we are able to then find the inverse. So I say all that to come back to our base function y equals sine x. If we find the inverse, we see that the domain is all reals, and the range was from -1 to 1. Or if you want to write that in interval notation, -1 to +1. So if we switch the x and y values, x equals sine y, and then if we solve for y, the idea of an inverse function is undoing that. So what we do is we take the inverse sine or arc sine of both sides. Those cancel each other out, and by cancel, they're undoing them. So we get y equals inverse sine of x. Now I'm just going to go to Desmos, and here we have our our sine function from -2 pi to +2 pi. If we look at this, it does not pass the horizontal line test. Subsequently, if we graphed x equals sine y, we're switching the x and the y, so we get our oscillating function over the y-axis. So the problem here is this is not a function. This doesn't pass the vertical line test. If I said x equals 0, we see, obviously, that it doesn't pass the vertical line test. So what we have to do is we have to restrict the domain of our function in order for it to be invertible. So what we're going to do, just like we did with y equals x squared, is restrict the domain of the sine function until it passes the horizontal line test. And what that does is if we zoom in closer and closer, we see that if we restrict our domain from -pi/2 to +pi/2, this is now a 1-to-1 function. So if we graphed the function inverse sine of x, we see that the domain is from -1 to +1, and that's what our y values are. So we switch the x and the y, and our y values in turn would be from -pi/2 to +pi/2. So with inverse sine, the domain is -1 to +1, and our range is negative pi over 2 to positive pi over 2. On the unit circle, what we are doing is we are solely looking at the right side of the unit circle with a little asterisk. This is 0, and what we do is we mark off our angles. So we have pi over 6, pi over 4, and pi over 3. But instead of being 3 pi over 2, which is spinning 3/4 of the way around the circle to get to 3 pi over 2, I'm going to just undo that. What we are doing instead is starting at 0, and we are working our way backwards. And this idea of working our way backwards is a negative angle. So if you recall, counterclockwise, or going up the unit circle, is positive. Going backwards on the unit circle would be negative. So we have negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. This gives us the interval for inverse sine. Just like we saw on the graph, we made it 1 to 1. So even though you're working with some angles in the fourth quadrant, the equivalent angle is actually going backwards. So that's the first key idea. So with our inverse function, what we're plugging in are values, and inverse trig finds the angle given the value. That's what we're doing. So let's look at some of these with a worksheet that I found. So it says graph and list the domain and range. And this is important. So we're going to graph our arc sine. We said our domain is from -1 to +1. And we have negative pi over 2 to positive pi over 2. Those are our intervals, and it's a portion of our oscillating function. Our cosine is similar, but instead of from negative pi over 2 to positive pi over 2, cosine allows us, if we graphed the cosine wave, that doesn't pass the horizontal line test, but if I restrict it from 0 to pi, it does. So looking at the graph of cosine, we see the y values are still from -1 to +1. So our x values are going to be from -1 to +1. But our outputs are from 0 to pi. So with arc cosine on the unit circle, we are just simply looking at the top portion of the unit circle. If we look at the inverse cosine graph, just turn that off, we see that our inverse cosine graph looks like this. So at -1, our output is going to be pi, and at +1, our output is going to be 0. So if we graphed inverse cosine, we have -1 to +1, pi, halfway is pi over 2, that's going to be 0, and we have 1, it's going to be 0 to pi. So our domain for inverse cosine is -1 to +1, and our range is from 0 to pi. For arc cosine, it's a little trickier because we have to remember that we have asymptotes, so we're only looking at one period, negative pi over 2 to positive pi over 2, and we get this interesting function in which the domain is all reals and the range is parentheses, negative pi over 2 to positive pi over 2. So if you're looking for help, inverse trig, sine and tangent are both in the first and fourth quadrant. Cosine, you should only look at the upper half, or the half semicircle, so the first and second quadrant. And most of the time when we're doing these types of problems, it is a scavenger hunt. So find the exact value for each expression. And most of these are going to be on the unit circle, so I'm going to pull up the unit circle to give us a little visual. This says inverse cosine of √2/2. So anytime it's positive, it's going to be in the first quadrant. Positive and let's just engage this one, positive first quadrant. And it's asking, anytime you see inverse trig, it's saying, at what angle do we get this value? So root 2 over 2, we look at the x value. Where is it root 2 over 2? We see that it is at pi over 4, and that's in our interval. Inverse sine of 1. At what angle is sine 1? And that's going to be at positive pi over 2. At what angle is tangent negative 1? So remember, tangent is y over x. So if we were looking from negative pi over 2 to positive pi over 2, it might be helpful just to change these values. Negative pi over 2, negative pi over 3, negative pi over 4, and negative pi over 6. Another interesting thing that you could do is note that tangent and sine are both odd functions, so you can just pull out a negative sign and only deal in the first quadrant. So this expression is equivalent to saying negative inverse tangent of 1. So tangent is saying y over x, where are the y and x values the same? That's pi over 4. Stick a negative in front, we get negative pi over 4. Let's say we're looking at inverse cosecant of 2. This would be the equivalent to inverse cosecant is the reciprocal of sine, and then if we take the reciprocal of 2, we get 1/2. And then this is just saying, at what value is the y 1/2? Well, we look at our unit circle. Our y is 1/2 at pi over 6, so our answer is pi over 6. Now, where it gets tricky is when we have negative values. So let's say we are looking at inverse cosecant of negative root 3 over 2. Well, as we said before, first or second quadrant for cosine. Cosine is the only thing that's different. So this is negative, so we're in the second quadrant. At what angle is the x value negative root 3 over 2? And we see that it's at 5 pi over 6. Now let's say, for example, this was a negative value. So at what angle is inverse sine 1/2? So we see that the y value is negative 1/2 in the fourth quadrant. Oftentimes, people are going to give the wrong answer as 11 pi over 6. And that would be wrong because, as we saw before, the outputs, the angles that will come out for the answers for inverse sine, in order for it to be a function, are only from negative pi over 2 to positive pi over 2. So what we need to do is find the angle that's equivalent in the fourth quadrant. So the equivalent angle would be negative pi over 6. And then these could get a little more involved. So what you could do is say, let's say we have a trig function on the inside. So we can work inside out. Tangent of pi over 4. Tangent of pi over 4 is root 2 over 2 divided by root 2 over 2, which is 1. So this is a fancy way of saying at what angle is cosine 1, which is 0. So any of these angles that are on the unit circle, we can do this. So inverse tangent is asking for an angle. The cosine of pi over 4, cosine of pi, what's the x value? Negative 1. I can do that little trick that we saw again. We can pull the negative out because inverse tangent is an odd function. And so at what angle is tangent 1? We just said is at pi over 4, and we make it negative, which is also in the fourth quadrant. Let's do a couple more of these. Inverse sine of tangent of pi over 4. We work inside out, so the tangent of pi over 4 we said was 1. At what angle is sine 1? We know that is at pi over 2. And this is, again, we're just doing a scavenger hunt on the unit circle. Sometimes, though, you're not given a value that is on the unit circle, and that's okay. So what we always do is draw a triangle. So in this case, we have our angle. It's positive, so tangent's going to be in the first quadrant. Opposite over adjacent, excuse my keyboard. So 4, 3. We know that's a 3, 4, 5 triangle, so the hypotenuse would be 5. And this is saying at what is the tangent of this angle? Well, tangent and inverse tangent are inverses. You see that 4 pi over 3 is in the domain. So if you just drew this triangle, the tangent of inverse tangent of 4 over 3 is 4 over 3. It doesn't change on the triangle. But let's say we have something that's not on our triangle or on our unit circle. So in this case, here's our sine of inverse cosine of root 21 over 7. So we go triangle first quadrant because it's positive. Cosine is adjacent, root 21, over hypotenuse. So to find the missing side, we would do 49 equals 21 plus x squared. So 28 equals x squared, which is 2 root 7 equals x. Now we can find the sine. So sine is opposite over hypotenuse. So the answer would be 2 root 7 over 7. Now let's take a look at a couple more of these. And since many of these are on the unit circle, we might have to look at a few that we might not have on the unit circle, but we'll ask for the exact value. All we're doing is finding the relative angle, I think is the terminology that the book uses, of where these are located. So inverse cosine of sine of negative pi over 3. So if I pull up this unit circle again, we go to negative pi over 3. So we start at 0, we go back. The sine is negative root 3 over 2. So at what angle, inverse cosine, at what angle is the x value negative root 3 over 2? Well, we know that this is negative, so we look in the second quadrant, and we're looking for the x value to be negative root 3 over 2, and this angle, therefore, is 5 pi over 6, because that is where the x value is negative. So what happens when you have, let's say, sine of inverse sine of 2? So many people are going to go, okay, we want a value. Inverse trig, we use a value to find the angle. So we had to say, is this in my domain? If it is, then these two should just undo each other and our value would be 2. So this is in essence saying, at what angle do you get a y value of 2? And we know from the unit circle that the y values are only negative 1 to positive 1. So this is an undefined function. Similarly, what happens if we say inverse sine, which is saying at what angle, of sine of 9 pi over 8? Well, we have to think, where in the world is 9 pi over 8 on the unit circle? So if we drew 9 pi over 8, we see that it's in the third quadrant. Let's say this is 9 pi over 8, because 8 pi over 8 would be pi. And we should think, what is the y value? And the y value here is negative. So we had to think, where from negative pi over 2 to positive pi over 2 would we get the equivalent y value? And the trick that I have seen is if we have to go backwards, how much do we have to go backwards in order to get back to pi over 8? Because that would be how much we would have to move down. And so 9 pi over 8 to get back to 8 pi over 8 is negative pi over 8. So our equivalent here would be negative pi over 8. And this is how you find the angle that has the same y value inside our output values. Similarly, if we said inverse sine, let's change that back to black. Inverse sine of, let's say, 2 pi over 3. Again, this is not 2 pi over 3 because they undo each other, but rather, we can do this problem from the unit circle. So let's pull up our unit circle, and we go to 2 pi over 3, and we say, what's the y value? So we see that the y value is root 3 over 2. So at what angle is sine root 3 over 2? Again, we pull back the unit circle and we say, okay, inverse sine, first quadrant, fourth quadrant. We know it's positive, so it's in the first quadrant. Where is the y value root 3 over 2? We see that's at pi over 3. So this is moving our angle into the output range that we would like to see. So let's try one more problem with that exact same type of logic. So let's say we're asking inverse sine of 5 pi over 8. Now, sine of 5 pi over 8 is not on the unit circle. So we have to think, where is this located? And if you think 4 pi over 8 is pi over 2, so it's a little more than pi over 2. So this is in the second quadrant. So I'm going to draw this. Here's our angle, a little more than we want in the second quadrant. So if we use the logic to get back to pi over 2, that doesn't really help us move backwards. I mean, we can. So here's the same type of idea of getting back to pi. So how much more would we have to move in order to get back to pi? And if we're at 5 pi over 8 here, then if we moved from 3 pi over 8 more, then we would get to pi, which would be the equivalent, if we're using the same type of logic, angle that we would have to get to. So at 3 pi over 8, we would have the exact same y value as 5 pi over 8. So instead of undoing themselves, we're finding the equivalent angle inside where we want it to be. So hopefully this clarified inverse trig a little bit more. If you think about it as a scavenger hunt, as long as you know where to look, you should be fine with this. If you have any other questions, feel free to email me.